Shut up and sit down.
Well, hey everybody, welcome back to 2020 National Electrical Code here on Patreon. And we are still moving forward in our definitions. Again, I can't emphasize how important definitions are and that you have a critical understanding. As we move through code, things become easier. But when it comes to definitions, it takes a little bit for us to explain them and talk through them. Now, a lot of people want to see graphics. I tend to not do that with definitions for a reason. Because if I'm talking to you and I'm explaining them, I am forced to have to explain them in a way that you can mentally understand it. And that's how I like to do it. And it's a method to my madness, but that's just how I like to do it. All right, so let's go on and get back into our definitions. And we ended up last time on luminaire. Now we're going to get into messenger or messenger wire. Now, many people, when I talk to them and I say, do you know what a messenger is? And they're not really sure what a messenger is. And we have allowance messengers in the National Electrical Code, and that is basically a support system from point A to point B. So in a building or outside of a building, I have point A, point B. It's a supporting system that cables or conductors are actually hung from. So when you hear people talk about a messenger, that's what it is. It's a supporting component. So what it says, it's a wire that is run along with or integral with a cable or conductor to provide mechanical support for the cable or conductor. So in a service drop, for example, you'll have a neutral that has got a steel, in many cases, it's a steel cord supporting neutral, and it has a steel supporting center core on the neutral conductor, or the grounded conductor in this case. And that is also supporting it as a messenger. Okay, so you have different types of cables that the messenger or the support system's built into it. And then you have individual messenger systems where you wire it from point A to point B, and you have what's called an aerial cable that is interlocked with it with a wrap that actually supports it from a messenger. So just remember that a messenger is a supporting system, a wire that supports it from point A to point B that's going to support a cable or conductor assembly from point A to point B. Okay. Now, messenger could be the whole assembly, or a messenger wire could be the wire inside of the cable assembly that's supporting the actual structure of that messenger. Okay, either or, they work synonymously. Doesn't matter. Again, as we said in other series, I can't cover every single definition, but we'll cover as many as we can cover that I think is pertinent to you learning the National Electrical Code. Motor control center. This is usually a big assembly, okay, and it contains control units that are designed to actually control a series of set of motors. So it comes all to what we call a motor control center. It's usually in one big frame. It's an assembly of one or more enclosed sections having a common power bus that runs through all of the sections that the enclosure or the componentry, the control features, connect into. Okay, and primarily contains motor control units, and it controls all the various aspects of motors downstream from a big assembly of motor control. And each one of those separate enclosures, okay, houses the control unit for a specific motor. Okay, so you think of it as a big square with lines and sections. Tic-tac-toe board. If you think of tic-tac-toe with that's inside of a piece of equipment, each one of those spaces are separate enclosure section. And each one of those spaces will have equipment in there that will control a specific motor downstream. Okay, that's a motor control center. And the reason we need to know that is because when you get up in 430 and things like that, it makes references to motor control centers and things like that, so you just kind of need to know. What is a multi-outlet assembly? Okay, well, a multi-outlet assembly is a type of service, flush, or freestanding raceway, and it's designed to hold conductors inside of it, and it has receptacles built into it. Okay, you've probably seen it. They call it like a plug mold. It is assembled in the field or at a factory, so I can buy it already made, or I can buy it in componentry and put it together because I have some that you can add to it. But it's basically, it's a surface flush or freestanding raceway. It qualifies as a raceway, the assembly, and it holds conductors in it. But it also has receptacles on it. And we need to know what a multi-outlet assembly is, because when we're doing calculations in 220, it makes reference to multi-outlet assemblies, and then, you know, depending on the number of receptacles on there, whether you're calculating for the amount of VA that's necessary, depending on the length. And all this is covered in 220, but you got to know what a multi-outlet assembly is. Basically, think of it as a track of metal with wires inside of it. It's a raceway, square raceway, if you will. Doesn't necessarily have to be square. I guess most are. Square or rounded front. And it has those receptacle plugs on it, spaced like every foot or whatever. Okay? That's an example of what's called a multi-outlet assembly. Neutral conductor. It's the conductor connected to the neutral point of a system that is intended to carry current under normal conditions. Okay? So a neutral conductor, if we have a Y scenario, so we have a center Y, and we have a winding this way, winding this way, winding this way. Okay, so that's one winding. If it's a 120, 120, 120 system, so it's a 120, 208Y, for example, then any of these points here that are connected to that neutral point, which is a center point between those lines, okay, that any one of them I measure to it, that's going to be a neutral, okay? But the neutral point of the system, and it's intended to carry current under normal conditions. So a 120 volt circuit, you've got two wires, black and white. You with me? Current goes out, current got to come back. If we're just talking just electrical theory, just very basic, okay? Then this way it is, and yes, it's alternating, goes both directions, but we'll just keep it simple. It's got to go out and got to come back. Go out, everything going out, it's got to come back. We have to have a complete loop system, okay? So the connection to a neutral point, out, okay, and that conductor is going to carry current under normal conditions, then that is a neutral conductor, okay? Now, what is the neutral point? The neutral point is that actual center point connection on, let's say, a Y-connected system, or the midpoint on a single-phase 3-wire system. So if I have a delta triangle, and I'm connecting just one of the windings, B to C winding in the middle, in order to get what we typically would have coming down to our house. It's a 3-wire system with 2 hots in the neutral. That middle connection point is the neutral point. In a Y system, whereas we have a center point and you have leg going here, 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 they're 120 degrees out of phase, then in that point, that is center point where all of these connect back to. That is the midpoint. That is called the neutral point. Okay? And again, informational note says the neutral point of a system is the vectorial sum of the nominal voltages from all other phases within the system that utilize the neutral with respect to the neutral point is zero potential. Okay? So any one of those Y's that I connect in testing from the end of that phase, say phase B or whatever, back, or phase A back to the neutral, then I'm going to get 120 volts. Okay? And that is the neutral point. Let's see here. Non-automatic seems pretty obvious. So anywhere in the code that I see a reference to something that says non-automatic, it means that it takes some kind of human intervention. I mean, I have to physically go and do something. So automatic, obviously, is without human intervention, but non-automatic means that, all right, it's not automatic. I have to. Now, interesting. A circuit breaker and a main breaker in a panel, let's say, that's non-automatic. Yes, it will function automatically on a short circuit, ground fault, or overload condition, but it has to be non-automatic so that I can physically shut it off, so it serves also as the disconnection means. Okay? So that would be an example of a non-automatic, but it does have functions in there that are very much act as automatic when it comes to things like overload, okay, or short circuit or ground fault. You with me? Okay. Some kind of intervention. Somebody's got to do something. Nonlinear load. Real important if you understand things like harmonics and the difference in what that can bring. It says, what is it? A nonlinear load, because you're going to see this reference in 220.61 for neutrals. You're going to see when sizing that, you're going to understand what the effects of things like harmonics can have with nonlinear loads. What is a nonlinear load? Because you need to know. If I'm doing this, and we know about harmonics, but somebody makes a reference to it, well, it's nonlinear loads. A linear load would be like a motor, okay? The waveform stays steady, okay? And it follows a normal waveform. Whereas the nonlinear load, not so much. It says, a load where the wave shape of a steady state current does not follow the wave shape of the applied voltage, okay? A nice waveform, okay? So the voltage does this, the current doesn't follow the nice waveform, right? What happens? What are some examples of this? Any electronic equipment, electric discharge lighting, okay? EDC, electric discharge lighting, things like that. Adjustable speed drive systems like variable frequency drives, and similar equipment may be non-linear loads, and they can create harmonic distortion, and they can raise the total harmonic distortions in a system, and it's something that engineers have to look at, okay? And it is going to play a condition depending on the type of system we're dealing with, okay? If it's a 4-wire 3-phase Y system, then we have to worry about things when we have a certain amount of harmonics based on a lot of the nonlinear load applications, okay? So important stuff that we have to be aware of, but we needed to know what a nonlinear load is. For example, a motor is a linear load, okay? Typical motor is a linear load. Now, the moment you throw an adjustable speed drive into the equation, which is going to change the voltage, it's going to up and down it and lower it, and that's going to also change the current because of the waveform changing, then you're going to have nonlinear loads, and you could have consequences, okay? The next definition is outlet. Well, we kind of talked about this earlier. What's an outlet? It's the point on the wiring system at which current is taken to supply utilization equipment. That's why we say lighting outlet, receptacle outlet. It is a point on the system where we're going to pull power from. Now, the reason we call it outlet like this is because it doesn't necessarily have to have a receptacle device in it, okay? I could hardwire something, and I connect it, hardwire something to that outlet is where I'm taking that utilization equipment and I'm literally connecting it to that source, that point in the system where I'm taking power from, okay? And so it could be hardwired, but again, an outlet box is at the point where the device can go in it, and I'm still taking power from that point. So the receptacle is a device that is going inside of an outlet. And we might put that together and call it a receptacle outlet. You just need to know the difference. Any point on the system where there's a box or whatever is considered, any point where we're taking power from that point is an outlet. And remember that. Now this is under Code Making Panel 1. So again, that reminds you that they're the ones that have purview over this definition and how it's designed. Okay. The next thing you might see in the code is outline lighting. What's outline lighting? Well, it's an arrangement of incandescent lamps, electrical discharge lamps, or other electrically powered lighting sources, could be LED, to outline or call attention to certain features such as the shape of a building or the decoration of a window. So when we're looking in the code, those buildings that have the lighting that shows you the outprint, you go down to downtown Dallas, for example, they have these lighting that shows the footprint, the outline of the building. That is considered outline lighting. So when the code makes reference to outline lighting up at 600 when it's dealing with signs and other types of things, just remember that outline lighting can also be something that accentuates something like a window or some other thing like window is a great example, but could be the doorway or whatever. That would be outline lighting. So if the code makes reference to outline lighting, you know what the outline lighting is, okay? And it can be incandescents, it can be electric discharge, it could be LED, any type of light source. that outlines to bring attention to it, okay, then, or used to decorate, then that is considered outline lighting, okay, when you're working in the code. All right, you've heard me reference this a lot, overcurrent. Overcurrent differs from overload, but everybody seems to get them confused because overload is a component of overcurrent. The easiest way to remember overcurrent is it's all these conditions that could raise the current over the operating level of the wire or the conductor or whatnot, okay, or the equipment, right? So what could do that? Well, short circuit could do it really quickly. The current really rises up and it's going past the rating of the wire or past the rating of the equipment. That's overcurrent. What about a short circuit condition where you have an ungrounded conductor that shorts to the metal raceway that's bonded or to the equipment grounding conductor or whatnot? Then you create, forget what I just said. Short circuit would be any of the ungrounded conductors connecting or making contact with another, I got one step ahead of myself, another ungrounded conductor. That's a short circuit, okay? Which again is going to cause the current to really, really, really skyrocket at the point of that fault, okay? That short circuit fault, and that's going to cause an overcurrent condition, right? It's going to exceed the wire's rating, it's going to exceed the equipment's rating, and that's why the breakers are designed to shut this thing down. Now we get to ground fault. Now that's occasion where any of the ungrounded conductors make contact with the metal raceway that's bonded or an equipment grounding conductor or whatnot. Now you create a direct ground fault condition. And of course, at that point, you have this little mini explosion and the current's going to skyrocket and it's going to exceed the rating of the wire or the actual equipment. So in order to protect everything, then we have an overcurrent protective device, and that's what it's designed to look for. And it has a certain trip curve and things like that that can be, usually for a circuit breaker, an inverse time, for example. The higher the current, the quicker it trips. But it's usually rated to be about 5 to 6 times its rating, and that's where it would trip, which is easily going to be achieved. If it's a 20 amp breaker and it's 100 amps, it's 5 times that rating. I can promise you that almost instantly in a condition of a short circuit or even a ground fault condition, that you're going to see a lot higher current instantly. And it's not going to affect the copper because it can handle a lot more current than what it's rated for instantly or for short periods of time. But it's going to allow that operation of that device to shut it down really quickly. And that's what it's all about. Okay? All right. Overcurrent protective device. We have branch circuit, and we see that referred to as a lot as a branch circuit. But you're going to see that that's just a reference to kind of the device, because you can also see what it's going to say in the definition. It says, a device capable of providing protection for service, feeder, and branch circuits and equipment over the full range of overcurrent between its rated current and its IR rating, or its interruptive rating that we talked about in a previous part. It says such devices are provided with interruptive ratings appropriate for the intended use, but not less than 5,000 amperes. Great exam question. It's always on an exam. If it doesn't tell you anything, it'll ask you what a branch circuit overcurrent protective device's interruptive rating is, and it's 5,000. Most of them will be at 10,000, and it'll be marked as such. But if it's not marked, just remember it cannot be less than 5,000. Okay, that is a branch circuit overcurrent protective device. Okay, it can't be less than 5,000. All right. Now, you're going to see other applications when we get to circuit breakers and fuses and how they might differ. But here we're just we're not going to get too far ahead because we're not differentiating right here between a circuit breaker and a fuse at this point. We're not differentiating. Now, when we get to circuit breakers under 240, you might see some differences. Okay, right now, let's just keep it simple, and it cannot be less than 5,000 amperes of interruptive rating. Okay. Be a good trivia quiz. Now, when we get to circuit breakers, you might see a little bit difference, but just remember, 5,000 when it comes to the definition. Next, what is a supplementary overcurrent protected device? Let me give you an example. So I could have an overcurrent device, and let's say I go down to a bathroom, and I have a piece of equipment that has a overcurrent device in it. And the general rule in 240 is that you can't have overcurrent protected devices in a bathroom. Okay? Okay. But if this is supplementary and the actual overcurrent protection for the circuit is upstream, this is just because it's part of the equipment or whatever in there, then it is considered supplementary overcurrent protection. Okay? And that might play a difference in whether or not it can be there or not. If it's supplementary overcurrent protection, okay, it's not required, but it's there, okay, then it might be different. So here's what it says. It says, a device intended to provide limited overcurrent protection for specific applications and utilization equipment such as luminaires and appliances, so it might be part of the appliance. It says this limited protection is in addition to the protection provided in the required branch circuit by a branch circuit overcurrent protected device. So it's there. So while the branch circuit overcurrent protected device might not be allowed a certain location, a piece of equipment might have a supplementary, and it might allow it to be there where it would not allow the primary protection. Okay? And again, it also reminds you that this limited protection is in addition to the required branch circuit overcurrent protected device. Okay? That's why it's called supplementary, if you will. Overload. Overload is a condition of overcurrent, as we've talked about. And what is it? It is the operation of equipment in excess of its full load current rating, or full load rating. I shouldn't say full load current rating. It just says full load rating. Or of a conductor in excess of its amperes that, when it persists for a sufficient length of time, would cause damage or dangerous overheating. A fault, such as a short circuit or ground fault, is not an overload. Okay? Important statement, because a short circuit and ground fault is not going to be of any sufficient time based on the overcurrent protected device. However, an overload condition can persist for a certain length of time, slowly raising the heat up, okay, where eventually an overcurrent device would detect it. Okay, but it's just equipment or conductors that are being utilized in excess of their ratings. Okay, and it's not going to trip as quickly as it would be for a short circuit and ground fault. That's why they make this statement here. It is not considered a short circuit or ground fault condition. It's an overload condition. It takes a little more time for something to trip an overcurrent device, which again is looking for the three things: short circuit, ground fault, or overload. Now, why is this important? Well, motors, for example, we have ratings for short circuit and ground fault protection. Okay, and that allows that breaker to be much higher than what the conductor would be. If you're not familiar with motors yet, we'll go over that in detail when we get there. But it could have, for example, a 50 amp rated breaker on a 12 gauge wire, and you're thinking, that cannot happen. That's just not supposed to happen. Well, you're allowed to do that in 240.4G, okay, under the small conductor rules. Usually it's 240.4D, which will tell you a 12 gauge has to be protected by a 20 amp device. Then, of course, you've got the little allowances in G, which says motors are different, okay, as an example. And so that's because you have the inrush and starting, but then it's going to come down to the normal running current, and it's not going to be that big of an issue. It's still going to protect it against short circuit and ground fault protection, but under the overload, it requires you at this point for a motor to have separate overload protection to take care of that portion of it. Now, there are allowances in there for the short circuit and ground fault protected device to also potentially cover overload as well. We'll get into some of that when we get into overloads and things like that. But just the general rule is that you remember that a short circuit and ground fault is not an overload. It is overcurrent, because it's going to exceed the current rating of those products or those wire, but it's not an overload. Overload takes a little more time, okay? And when you operate something in excess of its rating, then you have something that's going to break down over heat and things like that, and it can be dangerous due to that overheating, okay? All right, next, panel board. We're moving along pretty decent. What is a panel board? Okay, Couple things about panel boards. The panel board is actually the assembly, the buses, the devices, the overcurrent device in the main of a panel, all this. It's all the stuff that's built into a cabinet, okay? That's the panel board. The panel board is not the whole cabinet, okay? The whole enclosure, okay? So if you watched our video in this series when we talked about the definition of cabinet, you'll see there is a difference. You can have a cabinet, which is an enclosure, but the panel board is the guts, if you will, that is placed in a cabinet, okay, or a cutout box, okay? Kind of one of those things. Now, let's read the definition. It is a single panel or group of panel units designed for assembly in the form of a single panel, it's all put together, including buses and automatic overcurrent devices and equipment with or without switches for the control of lights, heat, and power circuits. It's the breakers and switches and whatnot. Designed to be placed in a cabinet or cutout box or cutout box in or against the wall, partition, or other support, and accessible only from the front. Okay, so panel boards go in cabinets or cutout boxes. Okay, goes in the front, and you actually access it from the front. So typically it'll have a dead front, which we saw the definition of in another video that we did here. And so that's it's the symbol guts. If you were to pull that out, you'd pull the main breaker out, you'd pull the bus out, and anything that's associated with it, it all come out. Okay, that's the panel board. That's the guts, and it's evaluated under UL 67, in case you ever wondered. Okay, and when it's put in a panel, they evaluate the cabinet. They evaluate the panel board inside of it. All of that gets evaluated. They'll actually rate the entire thing. And so just remember, the panel board is the guts, if you will, of the component. Okay? PV systems, photovoltaic systems, again, a total components, the circuit, the equipment, up to and including the PV disconnection means, combiner boxes, the inverters, that's what would convert the solar energy to electric energy. All of that's part of a PV system. Now, they could have gone in more detail. They could have said it includes the inverters, it includes the combiner boxes, but you might not always have a combiner box. So if you have 2 strings or less, you might not need a combiner box. You might just do that at a junction box or something. So this is probably the best term for it, but you know what we're talking about. PV systems, photovoltaic, those arrays that are on the roof, which are made up of cells in modules, made up of arrays that all go together in strings. You get it. Maybe one day when we get to PV, it'll all be clear on that. And I'll use graphics when I get there. We only use graphics when we start getting into the code material. All right. Piers. What is a pier? Looks like a new definition. Was covered over in, I think, 550. I think it was around in there. But you'll notice that this comes out of 303. So that is a direct result of being extracted and put in here for definition. So we need to know what piers are for 680 and 682 and things like that. We need to know what it is. So it's used in many articles, so we got to know. So, and when we're thinking about piers and we start getting into these things about the datum plane and all this kind of good stuff that we define. But what is a pier? It's a structure that extends over water and supported on a fixed foundation, which is a fixed pier, or on a flotation, which is a floating pier. We got definitions of those as well, that provide access to the water. Okay, so I'm going to go out on a pier. It's got a fixed foundation, or it's got a floating, maybe on these kind of foam floating, or maybe these oil barrels, whatever's floating, and that's a pier. Now, there's a difference between a fixed pier and a floating pier, and rather than go into the definitions, it's pretty simple. Obviously, a fixed is on a permanent fixed foundation, and a floating is inherently floating, okay? That it allows the structure to float on the water, which makes it rise and fall as the water levels change. You got to remember that a fixed one is not going to change levels when the waters change, okay? Very important, but good things to know. Plenum. Good to know what a plenum is. When we start talking about cables that get installed in environmental air, which is acting like a plenum, or what a real plenum is, it's important to understand what a plenum is in itself. And what is it? It's a compartment or a chamber to which one or more air ducts are connected, and it forms part of an air distribution system. So I like to give an example when I do a plenum. Let's say I have let's use this line right here on my flag. You can see it right here. Okay, that is a drop ceiling. So down here in the red that you see on my flag here on the screen, that is below the suspended ceiling. So here's the suspended ceiling. Now up here is the above suspended ceiling. Now let's say I have an air handler unit up here, and I have a return and a supply that's ducted in. Okay, so out of the supply to the actual air handler comes over and down, and there's a grate. It's sucking air from this space. And then on the output that's blowing it back down to the room, that's all ducted in as well, and that goes down, and that has a vent. So the air is being sucked up through the air handler and blown back down. So that's an all-complete system above this suspended ceiling, okay? So the plenum is the actual duct. The duct system up and into the air handler. I should go this way. Up into the air handler and then back down. That's a ducted system. If I penetrate that duct, then I'm penetrating a plenum because it's part of the airflow from one point to the other. You with me? Now, we're going to talk about what's called environmental airspace that acts like a plenum later when we get to 300.22. But just as a quick, because I don't want to leave you hanging, if that system above here has an air handler and one side is open and it's literally sucking the air from this space up here through a grate in the ceiling, which is sucking the space down here, it's just sucking it through up into this space, then this space up here is called an environmental airspace. It's acting like a plenum. And since it's acting like a plenum, then products would have to be plenum rated that goes inside of it, except under 300.22c, we get a bunch of products that tell me that I can put it up there, like MC cable, AC cable, things like that, that don't need to be plenum rated because it's inherently metal anyway, so it doesn't have to have a plenum rating on it, okay? Just like EMT, rigid, intermediate could go up there. You just can't have non-metallics up there. So that's a direct allowance. I get a lot of people that contact me and say that MC cable has to be plenum rated. And in that scenario, it does not, because that's an environmental airspace. Now, if you're going to physically penetrate a plenum, poke a hole in the side of the duct, or you're in a plenum. I've been in plenums that were as big as a room because it's a big cooling system and you actually walk into it. Then that is also considered a plenum if it's part of the air handling space. And then you got to worry about the stuff that's in it because it has to be plenum rated because you're in a plenum, okay? So that's a big difference than environmental airspace. Two different things, and we'll talk about that a lot more when we get to 300.22 when we're talking about environmental airspace and stuff like that. My point is, you can penetrate a plenum with interlocked, with limited distance. You can penetrate it with a smooth or corrugated MC. They can penetrate it. But you're generally only penetrating it for what reason? To get to a device that's sensing airflow. Or you need to get in there for some kind of device that is critical to the operation of that system. Otherwise, you don't go in a plenum. You don't penetrate a plenum. Okay? Now, plenum rated, if you wanted to get something plenum rated, then that would usually be NFPA 262, and that is a plenum rating. It's about density and combustible material and all this kind of stuff, smoke density and all that kind of stuff. Normal MC does not necessarily have to have that above a suspended ceiling. So stop asking for MC cable and above suspended ceilings to be plenum rated. It does not have to be. Stop the madness, people. Sorry. Let's go back to the code. All right, so I gave you a long definition of plenum. Okay, power outlet. What's a power outlet? It's an enclosed assembly that may include a receptacle, might include circuit breakers, fuse holders, fuse switches, buses, watt-hour meter mounting means intended to supply or control power to mobile homes, recreational vehicles, park trailers or boats, or to serve as the means for distributing power required to operate mobile or temporary installed equipment. So a power outlet kind of is an entire assembly that you might, and for the lack of a better term, it'd be something that you might see where you pull in your camper at a recreational park, right? Where you have the recreational vehicle, and it's got the plug in it, it's got a breaker in it too, all contained in this nice little package, this assembly. That is a power outlet, okay? We see these at trailer parks. We see these on marinas. Down on for the boat docks, those are called power outlets, and we follow 555 for the marinas, but those are called power outlets, okay? And they make them in a nice assembly, okay? Let's get into some of the more important ones here real quick. Okay, premise wiring. Okay, what is premise? Because you're going to see this talked about in the code a lot. Premise wiring. What is premise wiring? And you're going to be shocked to find out, okay? But it also includes things like PV systems and things like that into the premise wiring when we're applying the rules of premise wiring, okay? Let's kind of look at this real quick. It is the interior and exterior wiring, including power, lighting, control, and signaling circuit wiring together with all their associated hardware, their fittings, and wiring devices, both permanently and temporarily installed. This includes A, wiring from the service point, that's where the utility leaves off and the NEC begins, or where the electrician has to run it. Usually can be the service point on residential, could be if the utility drops the service drop from the pole down to the side of the building, usually at that point where the electrician has to run the wires or the cables or the raceways up to the weatherhead, that becomes a service point. Basically, remember, wherever the utility leaves off and I pick up as the electrician, that's my service point, okay? Could be at a pad-mounted transformer where they bring it to the primary and you're responsible for the secondary. That's the service point. So just wherever that service point is, okay? So it includes A, the wiring from the service point or power source to the outlets, or B, wiring from and including the power source to the outlets where there is no service point. Great example of that would be things like PV systems and generators and whatnot like that. So it comes from a generator, it's going to be a feeder, but it's also part of the premise wiring. And the point here is to remind people that because it is premise wiring, it was to make you to know that this all falls under the National Electrical Code. That's really what it's trying to say. When it mentions premise wiring, it's saying, look, if it's connected to the premise and it's connected to a power source, okay, then it is part of the premise wiring system, okay? It's not covering the stuff that's on, like utility, that's on the line side or supply side of the service point, okay? And if there's no service point, then it's not talking about a service at all. It's not talking about a connection to a utility, period. It's just other power sources. You with me? So it says, such wiring does not include wiring internal to appliances, luminaires, motors, controllers, motor control centers, and similar equipment. So what they're trying to tell you is, hey, we're going to cover, the NEC is going to cover all this premise wiring, all this wiring around the different things, to the different lights, to the different appliances, but we're not talking about the wiring that's inside of it. That's already been evaluated by the manufacturers and their nationally recognized testing laboratories components. We're not reinventing the wheel here, okay? We're not looking for that. So don't go cracking open a fire pump controller and go inside of it and start saying, these wires look too small. Now, if they've altered something, that's different. But if it comes this way, it is not premise wiring. It is part of that appliance, okay? It's a part of that motor. It's part of those controllers. Don't reinvent the wheel here. Now, if they modify it or alter it in some way, all bets off, okay? Now, an informational note just reminds us, again, that power sources can include, but they're not limited to, because there's other sources like flywheels and things like that. But anyway, it says interconnected or standalone batteries. Could have a battery source. You have solar photovoltaic systems, again, PV systems, or other distribution generation systems, again, could be lithium battery systems, it could be generators or whatnot. All of those are other power sources. So that's why this is written this way, because we need rules that cover these power sources that are also supplying into the system. We're just excluding the utility to this service point. That's all we're excluding, okay? Prime mover, probably important if you're looking at generators and you want to know what a prime mover is. It is the machine or the motor, for example, that causes the prime mover inside of a generator in order to generate the magnetic field. So you've got a generator, and in order for the generator to do what it has to do, it has to have a motor inside of it, and you have to exciter, and it has to generate this mechanical horsepower in order to generate current, okay? So it's the component that's going to drive the mechanical portion of the generator in order to get what we want out of it. So if you got a generator and you look at it and it's got a motor on it, that's your prime mover. You with me? Now, once that motor's going, then it creates a magnetic field, and you have an alternator and all this kind of stuff, and then you generate a magnetic field, and that's how you're generating current. Okay, so that's kind of the prime mover, is the machine, and it could be not just a motor; it could be some other source or some other machine that is providing that mechanical horsepower. So I don't want you to limit it to just a motor. That's the best example I can give on a generator, but it could be another source. Okay, that is a source. It's some other machine that could be the prime mover, causes that thing to happen, okay? Qualified person. Who is a qualified person? We hear this a lot in the National Electrical Code. Something's to be installed, maintained by a qualified person. It is one who has the skill and knowledge related to construction. You have history. You have background. It also says, and operation. So it's someone who has skills, knowledge in construction, and operation of electrical equipment and installations, and has received safety training to recognize and avoid the hazards involved. Interesting, great definition, because I know people that are qualified persons in what they do, but then they step outside of their comfort zone. They work on PV systems that they have never done before. They are not necessarily a qualified person, okay? I just use that as an example. So it doesn't mean that you don't step out of your comfort zone. You got to do something sometime. But usually you get trained, or you go through some training. You don't just step out and just do it. You've taken a PV class. You've done some kind of training. Then you do have the skills. Then you do have the knowledge. Then you can make you can do that job. But that's what it's talking about. Because if you don't go doing something that you're not familiar with, and the code requires that you be a qualified person, you're not qualified. Okay? A raceway. Now, typically, raceways, what's a raceway is defined in a specific article's definition. Okay? For example, a auxiliary gutter is not a raceway. It's an enclosure. Okay? But a wireway is a raceway. Right? And it says, an enclosed channel designed expressly for holding wires, cables, or bus bars with additional functions as permitted per the code. And when it says per the code, this code, it means that you might have added allowances within that specific article that's dealing with that type of raceway. And the informational note just reminds you, it says a raceway is identified within specific article definitions. So if it doesn't say it's a raceway, then it's not a raceway. You with me? So EMT is a raceway. Now, EMT is a tubing. It's not a conduit, but it is very much a raceway. IMC and RMC, intermediate metal and rigid metal conduit, is very much a conduit. PVC is a conduit. All of those which are still raceways. Okay? And we have what's called a communications raceway, which is designed, it's non-metallic material, and it's designed to hold communication wiring cables. Things like optical fiber, data, and all this stuff. It also holds class 2, class 3. and PLTC, which is power limited tray cable, and all this power limited fire alarm cables. And it typically is plenum, riser, and general purpose applicable rated. So look at your communication raceway. It's usually like an orange color or something. Doesn't need, it has to be orange. But usually it's going to be evaluated for those spaces. Okay. And it's considered a communication raceway. We don't run power conductors in a communication raceway. You'll notice that it specifically doesn't give me permission here to run class 1, which is typically close to identical to a power conductor. Okay? All right, so a couple other definitions that are real important, and we see this on the practice exams that I give people as well on our Fast Tracks program. Some of you might be involved in that. It is rainproof. Then you have rain tight. Subtle differences, both under the purview of Code Making Panel 1, but it is different. So what is rainproof? So it is, for something to be rainproof, it's constructed, protected, or treated so as to prevent rain from interfering with the successful operation of the apparatus under specific test conditions. Okay? So it doesn't necessarily mean that rain can't get into it. Right? It just can't interfere with its operation. It's not rain-proof. It's just, I mean, it's not, shouldn't say that again because it is rain-proof. It's not watertight. You know what I'm saying? It is rain-proof. It's designed. A good example is a NEMA 3R. Is an example where it does have weep holes in it. Okay? Things like that. But it's rain-proof. Okay? Now, it might also be rain tight. So the difference in rain tight is that it's constructed or protected so that exposure to beating rain, okay, which is different. Rain proof, okay, is not something, if the code requires it to be rain tight, then it has to be where it might be subject to a beating rain. So then that might be the NEMA 3R might have a component about beating rain, okay? You'd have to look, and we'd have to see the NEMA ratings of the enclosures to do that. But it says constructed or protected so that exposure to a beating rain will not result in the entrance of water under specific test conditions. So the rain tight means the water can't get in even under a beating rain condition. So rainproof, water could get in, it just can't interfere with its operation. Rain tight might be required where it's going to be exposed to beating rain and I can't have water enter into the actual system. And this all gets tested and gets a specific NEMA enclosure rating, okay? And obviously, we'll talk about NEMA ratings. I think it's 110.28 or something like that. When we get into 110, we'll look at these NEMA ratings, and then this will all come back together, and you're like, this all makes sense now, all right? Receptacles, important thing. A receptacle like we're familiar with that you plug a cord into, that is one type of receptacle. An attachment plug, like on the end of a cord, plugs into it, okay? But that is not the only type of receptacle. So we had to change this definition a couple cycles ago, okay? And we did it because they now came out with a device that is a receptacle. It qualifies as a receptacle because it has a male and a female that mate together and is designed to support things like luminaires, ceiling fans, or whatever. And it literally is a receptacle. It has a male and a female connecting component with blades that actually connect into the actual base. So in this scenario, it is truly a receptacle. So we had to change the definition. So what does it say? It says it is a contact device, receptacles are devices, installed at an outlet. So remember, we're putting a receptacle in an outlet, okay, for the connection of an attachment plug, which connects to that receptacle, or the direct connection of electrical utilization equipment designed to mate with the corresponding contact device. Like I said, you'll have one piece that goes in the outlet and one piece that might mount on the fan or the luminaire if it's heavy, and they come together and they click together and it has a supporting component, okay? And that is also considered a receptacle. It says a single receptacle is a single contact device and no other contact device on the same yoke or strap. That would be a single. that many people call a simplex. Okay? So it's a single receptacle. No other receptacles on that yoke or strap. Okay? Now, a multiple receptacle is 2 or more contact devices on the same yoke. Why is this important? Because you need to understand in areas of the code where it might say an individual branch circuit, and your allowances, like for a refrigerator to be on an individual branch circuit, and you have no other loads on it, then that might be a single receptacle. And that's just, kind of one example. Another application might be where I'm using the next size up rule, is that I'm doing a branch circuit and I'm supplying 2 or more receptacles, then I can't use the next size up rule. So it's important, because on machine and stuff, we're okay, next size up. But when we get down to branch circuits, this is going to be where it gets a little complicated. Of course, we're going to cover all that when we talk about the allowances to use the next size up rule. But remember, a duplex receptacle is literally 2 receptacles. Important to remember. But since they're on the same yoke, when we get over into commercial applications and we're doing a VA per strap, then it's 180 VA per strap. So even though there's 2 receptacles on one strap, you still only treat it at 180 VA. Now, since I told you that, I've got to clarify with you in the residential. We don't do 180 VA per strap in residential. I could put 50 receptacles on a 15 amp branch circuit if I want. Now, not practical. The code requires us to balance out our branch circuits. But could I? There's nothing that limits me for that, because they're not all going to be used at the same time. But we usually use some prudent design in a system, so typically don't do that. But I just want you to understand that there's no limitation with residential, but in commercial, there is a limitation. Okay? Now, a prudent designer will still use the 180 VA when they're calculating the number of devices in a residential, but nothing in the code says you have to do that. Okay? Just kind of making that clear. Now, you'll see that an informational note was added to explain exactly what I just said, that, again, a duplex receptacle is an example of multiple receptacles. Just remember that. It's going to serve you well later on when we make reference to a duplex, which is 2 receptacles. When something says 2 or more receptacles, then it really means 1 duplex. Or it could be 1 duplex or multiple duplexes. Okay, just make sure we're on the same page. Now, here's that term receptacle outlet. It's an outlet where 1 or more receptacles are installed. So, a receptacle outlet could have a single receptacle, which is just 1 single round receptacle, or it can have a duplex, which is 2 receptacles. That's why it says 1 or more. Okay? It could also have an outlet, a receptacle outlet, could be a 2-gang that has 2 duplex receptacles, which is actually 4 single receptacles. Sounds complicated, but it's not. All right. The next definition that's important is reconditioned. Why is this important? Because reconditioned was introduced in broader detail here in the 2020 code, because there's a lot of equipment in the code that prohibits you from reconditioning it. Like general circuit breakers that you see in your normal panel, you cannot recondition it at all. Okay? Now, switchboards and switchgears will have provisions for reconditioning. Okay? But like a low voltage circuit breaker, no. It's got to replace it. Things like that. Okay? Devices. Okay? Receptacles, if submerged, the manufacturers say it has to be replaced. But the point is, there are certain things that can be reconditioned and certain things that you cannot recondition. Now, this one wasn't without a lot of debate during the code development process. There was a lot of arguments about it, okay? But just know that you have a definition for it, and it's very broad. It says, electrical, mechanical equipment or systems, equipment, apparatus, or components that are restored to operating condition. This process differs from normal servicing of equipment that remains within the facility or replacement of listed equipment on a one-to-one basis. It also says, informational note, the term reconditioned is frequently referred to as rebuilt, refurbished, or remanufactured. So here's an important thing for me to explain. If I have a piece of equipment and it has a main breaker in it, a big breaker. Let's say it's a rack out type of breaker on a big piece of assembly. Okay, let's just say it's a switchgear. Okay, just for example, and I'm replacing a piece of component in it, one of those enclosures. Now, if I'm replacing it with another one that is just like it, but it's not that one, then that is not reconditioned. I don't have to worry about the recondition rules that we have in the code that you'll see about later, which means we have to make a label. The label's got to say when it was reconditioned, what was the date of reconditioning, who reconditioned. I don't got to do that because I'm not reconditioning. I'm doing a one-for-one change. Now, if I go into it and I'm doing servicing or maintenance while it's in place and I'm not taking it out of the facility, that's not reconditioning it. Now, if I take that piece and I send it to have it reconditioned, it's the same piece, and then they recondition it, and then they send it back to me, and then I install it back in, then it was a original piece that was reconditioned, excuse me, that actually goes back into the same piece of equipment. That's reconditioned, okay? And then all the rules of marking, labeling, identifying, and all that have to take place. And incidentally, you're going to find later that whatever the UL listing was on that piece of equipment originally now has to be removed, and the new listing has to go on it from whoever did the reconditioning, okay? Big change in that in the 2020 code. They just got to get rid of it, remove it, physically remove the other listing, and make sure that the listing now is applied based on it being reconditioned. That means it was now evaluated again. It basically loses its old listing, okay? No worries, because it's still got to be reevaluated, so it's going to be reevaluated. And the people that do reconditioned equipment understand this now. We're pretty much into this now, so it's not going to be complicated, okay? What is a remote control circuit? When we see something in the code, it's any electrical circuit that controls any other circuit through a relay or an equivalent device. So if I have to push button to make or break the contacts, let's say, in a starter, in a solenoid system, and I actually put to draw in the contacts to run a motor, for example. So that's a remote control. It is where I'm pushing it, and it's a circuit that's going to activate a relay that's going to bring in the contactors. The circuit that I'm wiring that controls the relay portion, that is the actual remote control circuit. Not the power parts that are feeding the actual solenoids that are, once it's kicked in, the current's going to be being drawn through it. No. It's the part that's controlling that activity. That's the remote control circuit, okay? Retrofit kits, again, is anytime, for example, I take it's a general term for a complete subassembly of parts and devices for field conversion of utilization equipment. So a retrofit kit, let's say I have a sign out in the field, and the sign is going from fluorescent or incandescent, the internal guts are going over to an LED. Then I would do what's called a retrofit kit to do this. And it's a list of parts and components that I'm converting this in the field, and it would be that retrofit kit. And you're going to see later on for those examples, then it would be a listed retrofit kit. But you just need to know the retrofit kit is designed to take one status and take it to another status, okay, through retrofit, okay? Like from an incandescent to an LED, if it was a lighting system. We see this a lot in buildings that have the old fluorescent, and now they want to change to LEDs, more efficient, due to ballasts are less efficient. So what happens is they'll go to an LED retrofit kit, and it's got to be a retrofit kit that is all subassembly of all the parts and components that can go in the field. I can literally pull the guts out and put it back up. That's an example of a listed retrofit kit, okay? Separately derived system. What is it? Now, we've talked about this before, and we're going to get into way more detail as we get into things like generators. So hopefully you're excited. This is a long series. And we're going to talk about separately derived system. But think of a separately derived system this way. There's no direct connection with the circuit conductors. Let me give you an example. Let's do a generator first. So if I have a generator, which again are not always separately derived systems, it's based on the transfer switch, and I'll show you. So if I have a generator outside, and I have the conductors coming into the transfer switch. Now into that transfer switch, I've got normal power, and I got the generator power, and it's going to end up coming out and feeding a panel, okay? So that the panel's running when it's on normal power. When something happens and it needs to go to standby, then that generator comes on, and the transfer switch will switch it, and now the power comes from the standby source, okay? Now, when we read this definition, it'll all become very clear. Remember what I just painted you. generator, normal power, transfer switch, and then the panel that's supplied by the transfer switch. Just remember that scenario. It says, an electrical source other than a service having no direct connection to the circuit conductors or any other electrical source other than those established by grounding and bonding, because we have to tie the grounding and bonding together. Okay, we have to do that anyway because of fault currents and ground fault and all that. Ignore that. We're talking about circuit conductors. Equipment grounds are not circuit conductors. People want to argue this until they're blue. They are not. The hots and the neutrals, those are circuit conductors. Equipment grounding conductors and bonding conductors are grounding conductors and bonding conductors. They are not circuit conductors. Okay? Important thing to remember. Now, they're run with the circuit conductors because we don't want to create some kind of inductive reactance application, but where you can generate heat and have problems. And we do have some allowances where you don't have to run the equipment grounds with the circuit conductors. In some allowances, I believe it's 250-130. So we'll obviously cover that. But for the general purpose, just remember, in our example, forget the grounding and bonding connections, okay? Because they will be intimate. Just think about the conductors. So we've got the conductors coming in from the generator to the transfer switch. We got the conductors coming from the normal power source to the transfer switch. And it's all of this is feeding another panel that's handling the standby. Now, if that grounded neutral conductor is not switched, which is the case in most residential generator setups, okay? It is not switched. It's just a solid bus. So the neutral from coming in from the service panel goes to the neutral bus. Same from the generator to the neutral bus, and then in a sense that also connects the panel on the load side. So that's called a non-switched grounded conductor, okay? If that's the case, that is not a separately derived system because that is a circuit conductor, the grounded conductor, that is not switched. So it is in direct contact with both the generator side, power source side for the normal power, and they're connected, they're intimate, okay? So that's not separately derived. Now, you put a transfer switch in there which actually switches not only the hot conductors, but also switches that neutral conductor, okay? If that's the case, now you have no direct connection between the conductors that are coming from the generator and no connection for the conductors that come from your normal source power. They're not intimate. They're not directly connected. So then that generator would be a separately derived system, okay? So that's a kind of an example of a separately derived. Now, let's shift gears. Let's talk transformers. Now, transformers, we're all familiar with that the grounding and all that has to be made up together because it all needs to be at the same potential. But when we have a primary winding and we have a secondary winding, they are not in direct contact, okay? They're very close. They are separated by some type of separate medium, okay? But they are not like a resin or some kind of paper or some kind of material, but the windings aren't touching, okay? They're in very, very, very close proximity, but they're not directly touching, okay? Because if they do, then it'll fault out and you got a problem with the transformer and the transformer's shot. But they're close. That is also a separately derived system. And transformers, other than auto transformers, which doesn't have a separation, has one winding and a tap on the secondary, taps a certain point on that winding, so that's not a separately derived system. But a true regular transformer like me and you are used to dealing with, you're going to have a primary and you're going to have a secondary. They are not in direct contact with each other. That is a separately derived system, okay? An auto transformer, they are in direct contact and they are not considered a separately derived system. In auto transformers, when we get to 250.30, we'll talk about it, totally different little beast, okay? But now you got a greater understanding of what's considered separately derived and what's not separately derived. Interesting fact, I don't know if I should go here, but when you have emergency systems under Article 700, you will have occasions where you better switch the neutral in those systems. Otherwise, you're going to have a problem because of the direction of current flow in a fault condition that you might not trip the GFP component that is in that system, and you could have a problem with it functioning properly. So you want to switch the neutral, okay? That type of thing. So topic for a different time, but just kind of making you aware of how this works, okay? All right, service. What is a service, okay? a service. It says the conductors and equipment connecting the surface utility to the wiring system of the premise served. Now, this can be from an overhead transformer. This can be from an underground service lateral. At the end of the day, all of that has to do with service because it's a physically, now we're going to have what's called service conductors underground, overhead, and we'll look at the differences in those. But they all are definitely service related. So all of those conductors that are going to intimately connect us to the premise wiring are service driven, okay? So just keep that in mind. It's a general overreaching statement, and then we're going to start breaking it down a little more here. All right, now, what's a service cable? It's service conductors made up in the form of a cable, like an SEU, an SER. Incidentally, the type U in SEU cable, you know, the ones with, you've seen it with the gray sheathing, and you have two conductors inside it with a helical grounded conductor in it. That is called a style U. And if you turn it on its side, it looks like a U, so it's easier to remember that's a style U. I think back in history, though, it actually was the U was called unshielded. Because back when it came out, you had either shielded or unshielded. And this is an unshielded. But most of us just say style U, which is kind of type U, what it looks like a U when you turn it on the side. But back in history, it was actually U stands for unshielded. But most of us today just say U for the type U. Style U is for the look. The reason is because you have an SER. And the R does not mean residential. It does not mean rural. It means round. Okay? So that's why it was easier for people to remember SER, round, SEU, style U. It looks like a U from the side. Okay? You see what I'm saying? So just different ways to remember it. But there's a difference, okay? But that's service cable, okay? Now, it's just some examples. Now, this also could be service cable, could also be MC cable that's used for service, okay? I can use that as a service cable as well, okay? So, again, under 230, you'll get a list of what can be used as service conductors, and it'll give you the different cable assemblies and all that you can use, okay? And obviously, we're going to cover that in detail when we get there. Service conductors is the so we had service cable and we had service, which is overall. Service conductors, what is that? It's the conductors from the service point to the service disconnection means. Okay, so let's do this. We're at a house, and outside of the house, I have a meter. And of course, you're going to find out in the 2020 code, you're going to actually have emergency disconnect out there as well. But we'll get there. We have a meter, and from the weatherhead, where the service drop comes from the pole, to the weatherhead on the side of the building where that service point is. Now from that point, down the wall, through the meter, into the structure, or over to the service disconnection means, those are called service conductors, okay? Just a general term. Those are service conductors, okay? So we're kind of laying the land out. You with me? All right, we're getting a good understanding of it. Now let's move on. What are service conductors overhead? Now, I'll explain to you after this why this is all important, but here's the difference. Okay, now, what is overhead? Because, again, it's service conductors. It's the overhead conductors between the service point and the first point of connection to the service entrance conductors at the building or other structure. Okay? All right? So, service conductors overhead. Let me give you another example of this. In order to understand what service conductors overhead is, we have to go down and look at what service entrance conductors are from an overhead system, okay? And then I'll tie the two together, okay? Trust me, I'll tie the two together. So we're going to jump down to here. So what is service entrance conductors overhead system? It is the service conductors between the terminals of the service equipment to the point usually outside of the building, clear the building wall, were joined by a tap or splice to the service drop or overhead service conductors. You with me? Okay. So the service entrance conductors are from your service equipment through the wall, up the side of the wall, which are also service conductors. Stay with me. Up to the point where the connection or tap gets made to something like the service drop. Okay, that's coming down. Okay, still at the point of attachment. All right. That, because it's coming from an overhead system, because it's coming from that type of system, then those from there, they're all called service entrance conductors, all the way down outside. Now, they are indeed service conductors overhead, okay? But more specifically, these are service entrance conductors, and that's usually from the weatherhead down into the service equipment. That would be your service entrance conductors overhead. Now, they're service entrance conductors, but they are derived from an overhead system, okay? Just follow me along. Now, what's the difference between service conductors overhead? Okay, what if I was running a system and the utility stopped at the pole on my property and they weren't going to run it over to the side of the building, right? Now, that point where they stopped, now I'm an electrician, I now have to run those conductors overhead over to the point, okay, from that service point, which is where they stopped at a pole at the edge of my property because they were too chinchy to run it down to my property. Maybe my house is 250 meters away and I have to run a bunch of poles. Anyway, I'm going to now run it, okay, and when I run it, that is what those conductors are called. From that point where the utility left off, all the way across through the different poles, getting to the point of attachment or the first point of connection to those service entrance conductors, which we just described, we're going up and up to that point of attachment on the side of the building. All of those are called service conductors overhead. Now, real quick, why is that important? Okay? Because in the National Electrical Code, you have the clearance heights that are in 230. They do not apply to service drop conductors. It's outside of our scope. That's utility. Now, inspectors still call it out. Utility's got you at the end of the day. The utility could say, forget you. I'm the utility and I'm fine with it. But when it comes to where they leave off and now you have to run conductors overhead, those are still service conductors. Again, right? I have to worry about clearances. So that's where we can get the rules for the height, 10 foot, 12 foot, 15 foot, depending on whether it's under a road or over a road or what. That's why it's important to know the difference, okay? Now, those that are running through the air to the side of our building that we had to run as an electrician because the utility stopped at a pole way back here, those are service conductors overhead. The moment it connects to the side of the building or makes that tap connection, then everything that's running down the side of the building also fall under what's called service conductors overhead. Okay? You with me? Now, same thing. Let's use that same scenario. What if I have outside, I have a pad-mounted transformer? Now, and here's my house with the meter. If the utility runs it underground all the way up to my meter, then that's what's called a service lateral. Okay? So they ran it all the way across, and I'm trying to see if I can, it seems like we actually, there it is right here. I just want to make sure we read it. Service lateral. So that's what that is, okay? It's underground conductors between the utility and the service point. So in my case, it's underground from their pad over to my meter. That's a service lateral. Outside of the scope of the NEC, totally. However, if at that pad, the utility stopped and said, you're on your own, the electrician's got to take it from here, then it becomes service conductors underground. And the reason that's important is because now I have to follow 300.5, the depth of cover requirements, where that didn't apply to service laterals if they ran it, okay? Now I have to meet certain code rules. So that's why it's important to understand it. Now, once I come underground and I come up and make a connection to the meter, then from the meter in, those become service entrance conductors, okay? And that's service entrance conductors from an underground system. You with me? Okay. Seems complicated, but it really isn't, okay? It's just, you really have to look and see where these conductors are coming from, all right? Now, service drop, again, is between the service utility, the transformer, down to the service point. That is the side of the building. And we many times refer to that as the line of demarcation. That's where the utility says, I'm done. It's yours now. So electricians, we will usually have to run service entrance conductors overhead out from our service, out through the meter, up to the side of the building. 10 foot, the drip loops can't be, have to be at least 10 feet above the surface, finished surface. and we're waiting for them to connect to it. We have to put a support there, an eye bolt or something, excuse me, for them to connect to, and then we just wait, and they make the connection. Okay, so it's important to understand all of these terminologies. Okay, and we'll cover this again when we get to it in 2:30, and we will have some graphics and things like that to talk about. Okay, don't worry, we're going to cover it. Just relax. It's all good. We're learning together. All right. Service equipment. Okay, it says, and you see there's been some changes. Okay, when you see this little notation here, it tells you there's been some changes. Some things have been deleted, added, whatnot. It says, the necessary equipment consisting of a circuit breaker or switches and fuses and their accessories connected to the serving utility and intended to constitute the main control and disconnect of the servicing utility. Why is this important? Service equipment. Now, you're going to see later on that we have some new allowances in the 2020 to have equipment connected on the supply side of a service disconnect, where we got to treat all that equipment like it's suitable for use as service equipment. It isn't a service, but it has to be treated like one, and that's for grounding and bonding purposes, okay? But we truly only have service equipment. When we think of service equipment, it is designed to separate us or disconnect us from a utility, okay? Now, again, we might have other rules in the code that say that things have to be suitable for use as service equipment. That doesn't make it, again, service equipment. It just says it's suitable for use as service equipment, so it could be used as service equipment, but you're using it in an application where the code just tells you that it has to be suitable for use as service equipment. But you might not be using it on a service, okay? That's a code telling you when to do something, okay? Make sense? Hope so. All right, so again, service equipment, it's your panels with your breakers in it and all that that's located, that your utility comes in, goes to the main breaker. Yeah, that kind of. Other thing to remember is meters are not service equipment at all. So never confuse a meter as being service equipment, because then it will confuse you down the road in certain things that we're doing. We obviously looked at service lateral. Service point. That is the point of connection between the facilities to be served, facilities of the serving utility and the premise wiring, where their wiring leads off and your wiring begins. Easiest way to explain that is on a residence. Usually it's the side of the building, and where the service drop comes down from the transformer, right there at the weatherhead, that you leave your wires hanging and the utility connects to it, hopefully, then that is considered a service point. Again, it's the line of demarcation between the utility, and their responsibilities will end and the premise wiring begins. That is your service point. It doesn't necessarily have to be to the side of the dwelling. I could have it again out at a pad mounted location on our property, whereas the transformer is a couple houses over. Now the utility runs it to a pad that's sitting on the edge of your property, and basically it's a big splice box, if you will. And they're saying, hey, we're done. You need to have your electrician bring his wires to right here. Well, if that's the case, those are service conductors underground, as we just saw, and the service point is right there at that point of demarcation, where the utility says, I'm done, and the premise wiring begins, okay? Next would be the short circuit current rating. This is what's required for apparatus, and it says it's the prospective symmetrical fault current at the nominal voltage to which an apparatus or system is able to be connected without sustaining damage exceeding defined acceptable criteria. So, piece of equipment, you'll have a breaker has its IR rating, it's on a panel board, and it'll be installed in a cabinet, and that cabinet will, as an assembly, it will have what's called an SCCR rating on it, and it should be equal to or greater than the available fault current, which is why we needed to learn what fault currents were as a definition, because any point on the system, all this different types of equipment all have different SCCR ratings. Granted, the further you get into the building, because of the impedance of the wire, which affects your fault current, then the fault current starts to drop dramatically. So I like to think that our wire helps out everybody. Okay, so in a sense, there you go. Just special permission. Anywhere in the code that requires special permission is actually written consent by the AHJ. So if it makes reference to providing you, for example, if you can bring more than one service to a building, or more than one feeder or branch circuit to a building, you have provisions for this in 225. You have provision for this in 230. There will be some allowances in the code where it says by special permission, and that is not by the AHJ. That's not the inspector just giving you their word, a handshake. You as an electrician need to demand that that's given to you is written consent. Now, many people have argued that a passing inspection on an application that's provided by the code that says you can do something by special permission, and you do that, and the inspector gives you a green tag, that is written permission. Every jurisdiction will be different. I'm prone to, if there's something that requires special permission and I do it, I typically like to get them to make some kind of statement on the inspection ticket that'll say in there, this inspection approved with special permission, or something to protect me as the electrician. Okay, just remember that if something has a provision for special permission, then that's the AHJ that's giving that permission, or the inspector, which is acting as a deputy for the actual AHJ in their capacity. Right? Standalone systems. Any standalone system is capable. It's a system that is capable of supplying power independently of an electrical power production source and distribution network. Okay, so it doesn't need something. It can do it on its own. It is literally standalone, self-sufficient. Okay, it doesn't need anything from a power production standpoint or from some type of distribution. It is literally standalone. Okay, that's what it is. So you're going to see things like standalone, which for PV systems has its very own. I believe it's I think it's 610. I'm not 100% sure. Now it's making me look. Hold on, folks. Because that would drive me crazy. Because, again, I have so many code cycles that I have to remember that I want to make sure that I'm right. No, 610 was not. Cranes and hoists. So I think it is. You might already know. I don't know. But it is under 6, so let's see here. Let's see here. I'm gonna go to the table of contents and look and see what it might be, because again, it drives me crazy because I should know this and I forgot it. You might know it already. You say, Paul, how do you not know that? I don't know, because maybe, just maybe, I'm human. And let's see here. That's cranes and hoists. Let's see here. It's taken way too long for me to find it. I hate how the index is laid out. 690, 691, 692, 694. Still looking. Oh, wait a minute. I was close. 710. Anyway, sorry about that. Anyway, 710, standalone, so it's easy to understand it. That's why it's important to have our code book while we're studying. Okay? A structure. What is a structure? It's as important because a structure, that which is built or constructed other than equipment. Why is this important? Because many people were taking situations where I had a piece of equipment that was on a pad, and because you constructed the pad, they were arguing that you needed a whole grounding electrode system and all that, and all it was a piece of equipment. So it didn't necessarily constitute a structure, because it was a piece of equipment, and that in itself didn't dictate that it was a structure, because once it's a structure, then we're required to do all this grounding electrode system, whereas really it was just a piece of equipment, and all we needed was an equipment grounding conductor to the equipment. Okay, so it's all important to differentiate that. Okay, surge arresters and surge protective devices, which are now going to be under overcurrent Article 242 of the National Electrical Code, which is combining surge arrestor and surge protected devices. Typical difference is a surge arrestor is usually always going to be on the supply side, that type of thing. So it's a protective device for limiting surge voltages by discharging or bypassing surge current. It also prevents continued flow, means it'll shut it off, flow of current through remaining capable of repeating this function, means it's repeats itself. It resets itself. Okay, so it's designed, that's a surge arrestor. Now, surge protective devices, very similar, and when we get to 242, we'll learn in more detail about this. But a surge protective device, typically surge arrestors are also what we would see sometimes up at the weatherhead. Can be on that anywhere. It's typically outside. That would make that connection. Okay, but you're also going to see that you have what's called surge protective devices as well, SPDs. So surge arrestors, and we'll talk about that in 242. But surge protective devices are critical because we did have a change in the 2020 code that's now going to require a type 1 or type 2 at all 1 and 2 family dwellings. And it's going to be located either type 1 or type 2. So it can be on the supply side or it can be on the load side at the actual service. Okay, or it can be downstream at a remote distribution panel if that's the direct panel downstream. So you have some allowances, but they have to be type 1 and type 2. Okay, and so here it says it's a protected device for limiting transient voltages. Again, big difference is limiting surge voltage on a surge arrestor, whereas you got a surge protected devices, it's also limiting transient voltage. Be honest with you, that can be surge current. That can be coming from outside, but it also could be coming from inside, okay? So there's a mutual contribution can happen with a surge current. Now, it says, handles limited transient voltages, transient meaning it comes and goes, by diverting or limiting surge current. It also prevents continued flow of following current, which remains capable of repeating these functions and is designed as follows. So there's a type 1, there's a type 2, type 3, and type 4. Incidentally, there's also a type 5, which is componentry driven as well. Not covered in here, not going to be what the NEC is going to deal with. So type 1 is a permanently connected SPD intended for installation between the secondary of the service transformer, so anywhere in there, and the line side of the service disconnect means. So this is one that could go outside. It could go out near the meter. This could go out up at the weatherhead. Anywhere between the secondary and the line side of the service disconnect. Anywhere in there, I could put a type 1. Probably not what most people are going to do. They're going to go with the type 2. Okay, I'm not saying all, but most people. And that is the type 2. It's permanently connected SPD intended for installation on the load side of the service disconnect overcurrent device, including SPDs located at the branch panel. Okay, so you're going to see that statement's important because there is an allowance downstream to a remote panel where you're going to have branch circuit devices. Okay, so feeders downstream. But for the most part, type 1s are going to be at the service panel. Now that can be in a breaker style. That could be immediately adjacent in a design that connects to the panel. You're going to see all of that in 242 and the rules that are associated with that. The point is, you're going to see that surge protected devices are now in the 2020 code are going to be required for 1 and 2 family dwellings at the service. Okay. Now, type 3 is point of utilization SPDs. That is like the strips that have the surge protection in it at your specific appliance or something like that. And then, of course, you have 4, which is a component SPD, including discrete components as well as an assembly. So it could have pieces or components that are built into something, okay? And that would be as a componentry type 4. Just important that you know where they are and you understand it. All right, and if you did want to know what UL standard deals with this, informational notes telling you UL 1449 deals with protective devices if you want some light reading material. All right, let's talk switches. Okay, switches. We have a general use switch. We have a general use snap switch. We have an isolating switch. We have a motor circuit switch. We have a transfer switch. Bunch of switches. What's the difference? Well, the reason we have all those, because throughout the code, you'll get many references, like can you use a general use snap switch to control a motor as a disconnect, and you'll get something that talks about general use switch, and you need to know what they are in order to understand the rules behind them. We got to know what that is. We know it's a switch, but there's a difference between a general use snap and a general use and an isolating switch. So the definitions are critically important because code reference might make some kind of reference to these types of switches. And if you don't know what they are, how do you know how to apply the code? So what is a general use? It is a switch intended for use in general distribution and in branch circuits. It is rated in amperes, okay? So 15 amp switch, 20 amp switch, and is capable of interrupting its rated current, 20 amps or 15, whatever, at its rated voltage. So it's probably a 120 volt, 20 amp general use switch. Okay? There you go. Now, how that differs from a general use snap switch. It says a form of general use switch, so it is a switch, general use, but it is constructed so that it can be installed in a device box or on box covers, or otherwise used in conjunction with wiring systems recognized by this code. Okay? So a general use snap switch is a device that is designed to go inside of a device box. Okay? Or it actually can screw and mount to the cover as a cover, a finished cover that goes over it, like a raised cover, and mount it. That is called a general use snap switch. Okay? Now the general use switch is a very broad. It could also be a breaker that is inside of the panel that is used as a general use switch. Okay? It's just important to understand all the rules here and know that there's a difference. But the ones that actually go in the box is a general use snap switch. Okay? Now, what is an isolating switch? An isolating switch is a switch intended for isolating an electrical circuit from the power source. It has no interrupting rating and is intended to be operated only after the circuit has been opened by other means. Okay? So, if I have a switch that is rated, that's being used as a disconnection means or whatever, if the code permits, and that's going to shut the circuit down, now we have an isolating switch that we're literally, it doesn't have a rating because it's not there for a rating. It's simply intended to isolate the electric circuit intentionally, 100%, the whole circuit from whatever it's supplying, okay? So it's not designed to operate like a disconnect. It's an isolating switch. It is in addition. It has no interrupting rating. It doesn't need to. It's not there to make or break. It is there to isolate the switch, the circuit, once it's been shut down by other means, okay? And there's some application in the codes which ask for an isolating switch, and you just need to know what it's doing, what's the function. Next is a motor circuit switch. You'll get this as well, where it's basically a switch that is rated in horsepower. It has a horsepower rating. It's designed to interrupt the maximum operating overload current of a motor, okay, of the same equivalent horsepower rating, okay? So, and if code asks for it, it'll ask for a motor circuit switch, and it'll say it's a switch rating, and it has a rating in horsepower that is capable of interrupting the maximum operating overload current of a motor of the same horsepower rating. So it's a 20 amp switch, 20 amp horsepower motor. As the switch, wait a minute, I don't like the wording here. I'm going to read it again because, again, these words. A switch rated in horsepower that is capable of interrupting the maximum operating overload current of a motor of the same horsepower rating as the switch at the voltage rating. Okay, so whatever the voltage rating is, the switch's voltage rating, the motor's voltage rating, horsepower rating, all of that in conjunction, then a motor circuit switch is rated in horsepowers as well as the voltage rating of the circuit for this motor. Then it can open it. Okay, It's a switch. The next is a transfer switch, and we talked a little bit about what a transfer switch is. Two different types of transfer switches. You can have a manual and you can have an automatic. What we like to refer to it here when it comes to transfer is either it's automatic or it's non-automatic. Okay? So the activation, the transfer process. Okay? So when I see transfer switch, it's an automatic, it does it on its own, or it's a non-automatic device. It means that somebody has to manually interfere with it and do something. Okay? For example, optional standby, you don't have to have an automatic means. It can be by manual means. So you need to know the loads that are involved in it when you're transferring a power, okay? Then you can do it that way. Whereas if it's an emergency or legally required, it's required to be an automatic transfer. So you have to do all these calculations, make sure it can actually handle the load on transfer and all this type of thing. That is an automatic. A non-automatic example would be an optional one where it doesn't have to be automatic transfer, okay? One of the other definitions we want to know is switchboard and switch gear, okay? What is a switchboard? It is a large single panel, frame, or assembly of panels of which are mounted on the face, back, or both switches, overcurrent, and other protected devices, buses, and usually instruments. These assemblies are generally assembled from the rear as well as from the front and are intended to be installed in a cabinet. So I have a big cabinet and I have the panel boards that are in it and I have switches on it, overcurrent, protected devices in it, other instruments, switchboard, okay? All in one cabinet, okay? Now, how does that differ from a switch gear? It's an assembly completely enclosed on all sides and the top with sheet metal, okay, except for ventilating openings, okay, inspections and things like that, and containing primary power circuit switching, interrupted devices, or both with buses and connections. The assembly may include control or auxiliary devices. Access to the interior of the enclosure is provided by doors, removable covers, or both, okay? So it's an assembly that is completely enclosed on all sides, okay, and the top. It's sheet metal. Ventilation openings, okay. Inspection windows, okay. But the switchboard is actually a frame, a panel, and things are mounted to it. A switchgear is basically assembly, and it does include auxiliary devices and controls and things like that. And basically, it's an entire rated assembly, okay? It's the best way I can explain it. The informational note might be a little better because I'm probably having a really hard time explaining the difference. Your engineer will call out whether something is a switchboard versus something that is a panel board. The other important significance is typically switchboards aren't over 1,000 volts, okay? And switch gear are typically will go over 1,000 volts, but not in all cases because you can have switch gear that's called a low voltage power circuit board switch gear, which is below 600 volts. So that's not the holy grail, but usually switch gear is probably not going to exceed 600 volts, okay? I mean, switchboards, excuse me, not going to exceed 600 volts, okay? And I guess that as we're looking up definitions, we could do a little search while we're at it. Let's see if I've got this up, and we'll see if we can do this. Let's see difference, and I remember it was up here, so we'll look between switchboards and switchgear. And let's get into common differences between switchboards and switch gears. We'll look and see if we have a reference that can do it a little bit better than me. Okay, so difference voltages. I don't know if you can see this on the screen, but one of the differences might be the voltages. It says switchgears systems have high voltage up to 350 kV, but switchboards are designed to handle to not more than 600 volts. So the voltage might be a limiting factor in that one as well. What else do we got? Different uses. Let's see what it says here. Switch gears are used to switch on and powering transformers, motors, transmission lines, generation and power networks for industrial, household, commercial, and distribution systems set up. Its purpose is to supply and control power to loads while also protecting it, whereas that's switchgear. A switchgear is also useful in identifying fault conditions and cutting power off. A switchboard is used to distribute power to multiple sources for transmitting it to individual loads like transformers, panel boards, and other equipment, control equipment like. So I guess a switchboard would be something that I would supply things like other panels. And since it's limited to 600 volts, that switchgear isn't limited. And I might use that to supply large distribution to other maybe other switchgear. Things like that, okay? Easiest way I can think that. Let's see here. Another example it says right here. We saw this earlier. This comes from the definition, but it's worth reading. It says switchgear consists of switching devices that are needed for low, medium to high voltage circuits. It is comprised of parts like fuses, lightning arresters, circuit breakers, isolators, relays, disconnect devices that regulate the flow of electricity. I got you. Whereas it says switchboard is a panel. That's why it says it was in a cabinet. It's a panel that has buses, switches, protective, and electrical control devices and are mounted on the back or front end or both. So they're mounted, you mount onto that. Switchgear is a part of the componentry involved in it. All right, so is there a chance that I butchered that one up for you? Maybe. The key for you is in the code when it talks about a switchboard, at least you know what it is. Now, if you get the piece of equipment because of the listings, it'll have to tell you whether it's switchgear or whether it's a switchboard. So this is probably a case when we get into switchboards and switchgear later on, I do have some graphics that will depict it. And my way of thinking it easily is that everything installs on a bus, on a panel, like a panel board or whatever you will, that installs inside of a cabinet. That's a switchboard. Which a switchgear has individual enclosures. Okay, it's separated by enclosures. Okay, the way I like to think of the two differences. Okay, all right, so that's all we're going to talk about in this lesson. And hopefully I didn't bore you too bad when we got to switchgear. This has been a long one again. So again, we got to get through these definitions. Hopefully you listen to them and understand them. Until next time, we'll see you in the next episode.
Shut up and sit down.